Okay, folks, I was a doofus and I paused the recording of this morning's lecture at the beginning because there was some idle chit chat. I was like, oh, I'll save everybody the trouble of having to skip over that. And then I never turned the recording back on. So there is no recording of today's lecture. And yeah, that's dumb. So I'm going to very quickly try to zoom through the main pieces of today's lecture. I'll definitely go faster than I did in class because I want to get something out is better than nothing. And with the exam due tomorrow night, I want to make sure that, that happens as quickly as possible. If you have questions about any of the things that get covered today, definitely ask. I apologize for the screw up. I will try to be more careful later on. I don't know if you can see in a meeting that the recording's paused, but if you can, and I make this mistake again, you should definitely holler, because yeah, that was dumb. So my bad. So there were two questions about the exam before we started doing kind of regular lecture. So I'll quick spin through those. The first was about split off term, which is theorem 8.23. So the question was about exercises like 8.6. So the short version here is, so this is split off term. So we have situations where we have things like P0 star P1 star P2 star ... star Pn minus 1 star Pn. Okay, and this is going to be written more nicely. This is the quantum of the star, not for all. Star over I, 0 at most I less than n plus 1, P of I. So we're saying we'll have P0, P1, P2 up to Pn. So I is greater than or equal to 0, so we'll start at 0. We'll go up to n, but not n plus 1. So we'll end here. And we'll compute all these PIs and collect them together with stars. And that star is completely unreadable nonsense. So let's fix that. Because that just looked like a spider died on the screen, and that's not helpful. Okay, that's not a lot better, but it'll do. And so theorem 8.23 gives you two ways to separate these things out. One is to take all this and split off a term from the front, and the other is to, split off a term from the end, and the other is, part B is to split off a term from the front. So this is B, and this part here is A. So they both say we can take a quantifier that goes from 0 to n and rewrite it as a quantifier that does almost all of it and then the last one, or the first one and then the rest of it, okay? And so if we think about A, for example, 8.23a says star I 0 at most I less than n plus 1, P equals, so that was this part here, star I 0 at most I less than n, so an n here instead of an n plus 1, P, and this is that part there. And so then we've got to tack on this last bit, which is star P with I replaced by N. So we're going to take whatever P was and replace it with N. Okay. And then we did an example quick of exercise 8.6a. Exercise 8.6a, where I started with the complicated side because there's more structure. So we had, which is the right-hand side here. So we had or I, or exists I, depending on how you want to read that. 0 most I less than n plus, oh, just n, sorry. bi equals 0, or bn equals 0. So here P is bi equals 0 and star is or. And with those two substitutions, this matches that, or is star, and this is that. So we can take all of this and rewrite it to the other side using 8.23a, and we get for or I, 0 at most I less than n plus 1. P is b of I is 0. And we're done. That's actually the whole proof. QED. And these split off term proofs are usually about this simple. Sometimes there can be some range manipulation that you need to do to make things match on either the front end or the back end. But other than that, they're usually kind of about that easy, okay? So hopefully that's helpful. The other question was about range or body weakening strengthening. So it was essentially to do one of the range weakening strengthening problems from chapter 9, where you had an implication in the theorem instead of an equivalence. And I did exercise 9.23, which says there exists X RP implies that there exists X R P or Q or R. Q or R P. And with these problems, we almost always start with the more complicated side. So we'd start with there exists X, Q or R P. And now the first step in these is usually a chapter 8 rule. So in which chapter 8 rule depends on whether we're trying to break the range apart or the body apart. So there are some of them have, the complicated side has an and or an or in the body, and some we have, like in this case, an or here in the range. And so if you're doing a, if the body is the complicated part, then you're probably going to use 8 point, sorry, need my paperwork, coping badly. 8.15. So if the body is the complicated part and the operator matches the operator in the quantification, then 8.15 lets you split the body up into 2 quantifications. If, on the other hand, the range is the complicated part and it's an or, like it is here, then one of the range split axioms, 8, 16, 17, or 18 would be the one to use. And if we're doing chapter 9 theorems, it's almost always going to be 818 range split for idempotent, because we're doing either exist or for all, and those are either or and and are idempotent. So that's the easy one to do. So here, that would be, we would use 818. And we would get exists x qp. And now star here is going to be or, because exists is or. And then exists x rp. And now this is nice because this matches this exactly. So it's like, woohoo, we have the thing we want. Now we got to get rid of this part. And if you're proving one of these chapter 9 weakening and strengthening rules, you almost always end up using a chapter 3 weakening and strengthening rule. So usually either 376A or B, depending on which direction you're going. Is it an or is it an and? And in this case, it's an or. So we're going to go from the or left ways. And that's good because we're going from here to there. So it needs to be that this follows from, and then we'll have 376A, which says thing or thing follows from either one of the things. So we'll do that follows from XRP, and we're done. So first step, you're usually using either 815 or one of the range split rules, 16, 17, 18. If it's chapter 9, you're probably using 18 because everything's idempotent and life is good that way. That splits you up into something like this. And 815 would split you as well. And then you use some chapter 376 thing to either follow from or imply the thing you're after, depending on which direction your arrow is going. Okay, so hopefully that was helpful. I keep wanting to stop and ask if there are any questions, but that's not going to help now. So then after that, I did a number of examples of translating from logic to English. And these were a little complicated. So I'm hopefully going to be able to sort of do these justice here. But definitely ask questions if you're like, man, I do not know what you meant by half of that. So I'm going to do exercise 9.30B, which says there exists a Z in R such that for all I in the integers, f of j equals f of j plus I times z. So as I said in class, this is, I think, in some ways, one of the hardest problems. It's an interesting problem. It's a cool problem. Like, it leads someplace interesting, but it's not at all easy. And it's definitely harder than any of the ones that are in the homework. So I want to do it because it's interesting and because I think it illustrates some interesting things, but don't freak out. You're not going to have to do something this complicated. So first thing to note is there's no quantifier around J. J is just coming in from the outside, which means in some sense, kind of implicitly, this is true for all J. It's true for any J because we don't know anything about J. So it'd be like a person has a heart. Like, we don't know anything about that person. So in some sense, we're saying all people have hearts. And we don't need to quantify over that, right? We're converting to English, but it's important to realize that this is sort of essentially true for all j. Now, if this is true, we can actually look at some particular values and see what sort of things happen. So in particular, if we think about f of 0, well, this says f of 0 is f of 0 plus 1 times z, or f of z, right? And this is f of 0 plus 2 times z, or f of 2z. And in fact, it's equal to f of 3z and 4z and et cetera forever. So f is the same at 0, z, 2z, 3z, 4z. That's implied by this. And similarly, if we looked at f of 1, we'd have, that's the same as f of 1 plus z, which would be the same as f of 1 plus 2z, which is the same as f of 1 plus 3z. Okay, so f of 1, the f is going to be the same at 1, 1 plus z, 1 plus 2z, 1 plus 3z. And one way to think about this is graphically, if this is j and this is f of j, okay, if we just pick a value for 0, for f of 0, and it doesn't really matter what value we pick, we just need to pick, I'm just going to pick something. Obviously, you know, the reality might be different, but I'm looking for kind of what's the pattern going to be here. So if I say this is f of 0, then what we know is we know that f of z, it's going to be the same value. So if this is, switch back to black. If this is z, and this is 2z, and this is 3z, and this is 4z, etc., we know f is going to come back and be the same thing here and here and here, and in fact, every sort of z apart, okay? And we could then look at f of half of z. So we could say, well, what's f of half of z? So if this is z over 2, and I'm going to just pick a value. Who knows what it really is, but let's say f of half of z is down here. So what that tells us that f is going to be down here halfway between all the z's. So it'll be here, it'll be at z plus half z, 2z plus half z, 3z plus half z. It'll be in the same place all the way forward. And if I do one more, and let's say I do z over 4, and let's say it's up here, okay, then it's going to be up here everywhere along the way. And if we keep doing this, what we're going to end up seeing is a pattern that's going to look something like and the shape you're going to get depends on the choices you make, but the important thing is it's going to keep repeating itself, right? That it's going to go through and keep going through the same values over and over again. Mine's not very good because my handwriting isn't awesome, but you get the point, right? That this is going to go through the same set of values over and over and over again forever and ever and ever. And what that tells us in mathy terms is that F is periodic. So if you've taken like a trig or a pre-calc class, you've seen things like sine and cosine, tangent. Those are all classic examples of periodic functions. There are others. And periodic functions are very important in modeling real world phenomena, things like the seasons and the impact of the moon on tides and what are called lost the name for it, but there's a term in biology for things that are periodic in the behavior of biological organisms. And there are organisms that have annual cycles and monthly cycles and daily cycles. And so we would model all of that with periodic functions, okay? Or another way to think about this is that F repeats itself every Z, right? That's a little fuzzier. It's also worth noting that if you wanted to capture this fact, this is periodic with period Z. Because F does whatever it does from 0 to Z, and then it repeats itself from Z to 2Z, and it repeats itself from 2Z to 3Z. So the period, the length of the bit that repeats, is going to be Z in this case. Okay. Okay. So that's that one. Let's zoom ahead here. Exercise 9.30C we did in class on Monday. So I'm going to do exercise 930F. Oops, 0F. And the thing here is for all X in R, there exists Z in the integers such that F of X equals Z. And this is essentially just saying that for every input to the function, the output is an integer. We could say, something like F is an integer valued function on the real numbers. Or F maps every real to an integer, right? I mean, these things are always a little fuzzy, and there's usually a bunch of plausible ways to write these things, but those would be two possible ones. If we want to think about it in terms of graph stuff, if this is X and this is F of X, what this is going to tell us, the fact that F of X is always an integer, means that instead of F of X being some curve that moves smoothly through space, or even something that like hops in some interesting ways, this is going to hop in some very particular ways. So if this is 1, this is 2, this is 3, and this is -1, and this is -2, etc., that F is going to always take values that are on these lines, right? F is never going to be between the integer values. It's always going to be somewhere on one of these horizontal lines, because it can't ever be 1.5 or -2 1/3 So it's always going to be on one of these horizontal lines. So even though we allow real numbers as inputs, the outputs are always integers, okay? So then the last 9.3 that I did, exercise 9.30H, is for all little z in the integers, little z is even. There exists w in the integers where w is odd, such that z equals w plus 1. So now what does that translate to? Oh, actually, I'm going to make a couple of notes right here on the thing. So first thing to notice here is that, and this one, I don't think graphing actually works very well here. You could, but I'm not sure it would be informative, but your mileage may vary. But it's worth noting that this is saying for all even integers. And this is saying there exists an odd integer. Okay. And so we want to translate this. I'm going to actually start with a fairly brute force translation, and then we'll clean it up a little bit. So brute force. For all even integers z, there exists an odd integer w such that z equals w plus 1. Okay. Now, this is not great. And it really doesn't have the property, like it doesn't sound like a thing people would say in conversation. And one way to tell that you haven't really gotten there is it still has variables in it. People don't tend to talk and use variables in speech, right? We don't use variables when we're having a conversation with other human beings. Maybe that's a bad thing, right? And maybe we should, I don't know, right? We could have that debate. But it's certainly true that if you introduce a variable into a conversation, people tend to be like, what are you talking about? If we look at the English in exercise 9.29, for example, most of those don't have variables in them, or many of them don't have variables in them. So you have things like some integer is larger than 23. We don't have a name for the integer. That's part of what we have to do when we formalize it. A positive integer is not negative. We don't have a name for that. We have to come up with that. No integer is larger than all others. We don't have a name for that. So that's actually pretty common, that in English, we don't tend to have names for things. And when we formalize them, we need to create the names. Well, the flip side is that when we're going from logic to English, we often want to get rid of names, that names are a sign that we haven't really captured the English language version of things very well. And so the fact that we still have Z and W here is a bad sign. So that what we really want is something that doesn't have those variables in them. So we want something that's more like every even integer and then what's the relationship? Oh, I left out the plus 1 here. what's the relationship between the even and the odd? Well, the even is one more than the odd. So every even integer is one more than some odd integer. Okay. And so the some odd integer is like this part here. The is one more is that part there. And the every even integer is this part here. Okay. So that would be, I would argue, a better translation of that quantifier to English than the brute force one. And one way to tell that we've sort of done a pretty good job is the fact that this doesn't have any variables anymore. Okay, on to another example. I keep wanting to pause and wait and let you think and ask questions. Not making sense. Did a example 9.32c from the book. So the first thing, oh, and I guess I should write the thing down. So no student who has received an F in a required course graduates with honors. So the first thing I'm going to do here is I'm going to sort of work out some predicates. And we went into this in a little more gory detail in class, but I'm going to try to keep it short here in the interest of saving space on this slide so it'll all fit better, but also in terms of time. So we need a couple of different predicates, or three predicates. So we need something about receiving a grade in a course. I'm going to leave required out for a second because we're going to receive grades in all our courses, not just in required courses. So it being required is sort of property of the course, not the grade. So I'm going to make a separate predicate for that. So I'm going to have a got grade SCG is true if student S got grade G in course C. And there was a question in class about the order of the arguments. Doesn't really matter. I did it student course grade. If you want to write it student grade course, fine, as long as it's clear from your description what that means. We're all good. Required C is going to be true if C, course C, is required. And then grad with honors. You could split up the graduating and the with honors part. I'm going to actually just do them both together because we don't have a need for them to be separate here. So that's going to be true if student S graduates with honors. Okay. Now, the translation, no student suggests to me there does not exist a student S Now, we're focusing on the graduates with honors bit. We're saying no student that does something graduates with honors. So I think we want graduates with honors down here, which I'm going to just write in English for a second. Because we're saying no student that does a thing we don't like graduates with honors. Well, what's this thing here? It's they received an F in a required course. S received F in a required course. Okay. So then now I need to turn these Englishy bits into less Englishy bits. Now this we actually have a predicate for. Grad with honors S will take care of this part here. So we could do a step here where we just leave the range alone. F in a required course. Grad with honors. Okay, so that translates this part to one of our predicates. Now we got to do something about this. Now, this is student. So S received an F in a required course. That means there must be a course C, right? Notice we're missing a name for a course here. So we're going to need to introduce a course name. And we're saying there is some course they didn't do well in. So there exists a course C such that, well, there's two things. C is required and S received an F in the class. So we could say, and because of trading, there's a bunch of ways we could do this, but we could say there exists a course C such that C is required and got grade So got grade takes a student, a course, and a grade. Well, the student is S, the course is C, and the grade is F. So this part here is matching this part here. It's the translation of that piece there. And then we add the grad with honors, which I'll abbreviate because I'm running out of room. There, and then we're done. And so that translates, no student has received an F in a required course, graduates with honors. No student, right? No student graduates with honors who has received an F in a required course. Okay, questions? Habit. Okay, hopefully that helped. I apologize profusely for not having captured the video. I hope this is still useful to you. Yell at me if it's not. If you got any questions about any of this, definitely let me know. And you might just start asking me at the beginning of class moving forward, dude, are you recording? Because we sure wouldn't want to have this happen again. So sorry about that. Thanks a lot for your patience, and hopefully this helps. Talk to you later. Bye.